I was just trying to do it. So, can someone lead us in order of prayer before we can begin? Senior files, anyone to pray for us? Yes, Mildred.
Our Father,
Gracious
our
God
Father
of
who art
King of Father, our prayers are going to begin now. Let's pray. Gracious God of King of Father, our prayers are going to begin our lesson. May you help us to understand. May it not disturb us and help us remember whatever He has going to teach us. I pray in Jesus' name I pray. Amen.
Amen. Thank you so much, Mildred. So, before we begin, today I had prepared for us to study about radioactivity. I don't know how many of us had started covering it in our various schools, but that was my preparation for today's lesson. But of course, I can know what topics to look at maybe in our next meeting so that I can plan prior. So I wasn't able to communicate with us on that. So may I know what topics we had covered? Because I know most of us reported to school a bit late and we weren't able to cover as much this term. So maybe in the chat, may I get some responses on what we were able to cover? Okay, for negative properties, gas laws, claims mechanisms or problem. Okay, for mechanisms, there is no shortcut. You just need to practice them. They're like calculations. You have to keep practicing them. Colligative, isomerism, atomic structures. Okay, that is good. So for those of us that covered atomic structure, that means radioactivity will, and even those who haven't covered, really, it will be a smooth flow. Okay, so at least we had covered something. Colligative properties, gas laws, atomic structure. That was a very good start for all of us. So I'm going to be sharing how should I call it, from our text, but of course where we have questions and where I need to illustrate, I'll keep popping up the whiteboard to explain a few concepts here and there. So we've all heard about radioactivity, at least in our O-level physics or somewhere, or some people always read ahead. What is radioactivity? Or what comes to your mind when you hear the word radioactivity? Anyone who has an idea? Yes, Nelly.
Good, good evening, madam.
Good evening to you.
I think radioactivity is the spontaneous disintegration of a radioactive nuclide with emission of energy.
Okay. Thank you, Nelly. That is good. Anyone else? Okay, so when we are looking at radioactivity, uh, you're looking at that spontaneous disintegration because remember it's a radio and then an activity. So that means you're looking at that spontaneous disintegration of an unstable heavy nuclei or nucleus to form a light and stable nucleus or nuclei. So those words are very important as you define what radioactivity is. Spontaneous disintegration, that is, those are two. Then heavy, unstable nucleus to form light, stable nuclei with emission of energy. Because every time you're disintegrating these different particles, you're emitting what? Energy. So if you're emitting energy, maybe before I share my note screen, I'll just share something with us here. Okay, so I was still explaining and I said, when you're looking at a spontaneous disintegration, we have of an unstable. So when you're looking at this unstable nuclei and emission of energy, that's where I want to really put my emphasis. When you're looking at the emission of energy, that means every time you're disintegrating a given particle, you're emitting energy. And this energy is in form of different particles that as a result of that emission. So when you're forming the stable and light nuclei, there are particles that are being given off at that point. So those particles exist differently. And I want us to give suggestions on what those particles are. What are some of those particles of energy that are emitted during the emission of energy? I know we've heard of some of them, so you can just give us what you think. Okay, I can see in the chat, alpha particles, good. Yes, Phoebe.
Beta particles.
Beta particles, very good. What else?
And also gamma particles.
And also gamma particles. Thank you, that is very good.
Gamma
So,
rays.
yes, we have the gamma rays. So, these are the three basic particles that are emitted during the spontaneous disintegration of that nucleus. So when you're looking at those particles, when we are looking at the alpha particles, the beta particles, and gamma particles, they also have properties that cause them to be emitted the way they are emitted. So when you're looking at the alpha particles, there are those properties that induce it to be what? To be given off. And then the beta particles, same thing. And then the gamma rays, the same thing happens there. So what are some of the properties of the alpha particles? What are some of the properties of the alpha particles? Anyone who has an idea? Yes, Phoebe?
They are positively charged.
They are positively charged. That is very good. Rebecca?
They have the least penetrating power.
They have the least penetrating power. Very good. Latif?
They are made up of helium nuclei with a charge of positive 2 and mass number 4.
Okay, that is very good. So they are made up of the helium particle or the helium atom, which has an atomic number of positive 2 and an atomic mass of 4. Okay, good. Nelly?
They are stopped by thin sheet of paper.
They are?
They are stopped by a thin sheet of paper.
Okay, they are stopped by a plain sheet of paper, which shows that they have a low penetrating power. That is good. Any other? Please, when you finish giving the answer, can you please mute your microphone because it keeps sending a lot of feedback. Okay, the person using my screen, can you please behave? Okay, so there are a stream of helium nuclei. I can see the chart. Okay, so when you're looking at alpha particles, first of all, you need to understand what they are comprised of. And like our friends have told us, you're looking at them having a helium particle. And that helium particle is made up of a mass number of 4 and an atomic number of 2. So in most cases, you'll find that that atom is represented by this particle. So when we have this particle here, sometimes you'll find the alpha demonstration. But in most cases, when we are giving the properties, we define it as a helium particle, which has an atomic number of 2 and an atomic mass of 4. So that is how we represent the alpha particle. And then when we move to the other properties, it has a low penetrating power. That's why it can be stopped by a small sheet of paper. So it has the least penetrating power of all the 3 particles that we are looking at. And then when we move to its charge, you realize that it's positively charged. So among the 3, we find that it is positively charged. I don't know if the people writing on the screen are intentionally doing it or they're exploring. And then we have, because you disorganized my explanation, so please stop it if you are doing it. Then we have also the fact that it's deflected on the negative side of the plate. So that means it's deflected negatively on a magnetic plate or on an electric field. So because it is positively charged, that means it will be deflected in the opposite direction. Like I'll show us in the notes that kind of diagram that shows the deflection effect. So during deflection in the magnetic field or in the magnetic field, it is deflected negatively because of being positively charged. So I think those are the key properties of the alpha particles that we need to be conversant with. Then, of course, we move on to the beta particles. What happens with the beta particles?
They are deflected to the positive pole.
You, Derek, but when you say positive pole of what particularly, so you need to be specific of either the electric or magnetic field. Betty, please mute your mic unless you're giving us an answer. Okay, let's hear from Latif.
They have a negligible mass number.
They have a negligible mass number. Okay, good. Rebecca?
They have a fairly high penetrating power than that of alpha.
Okay, good. So their penetrating power is higher than that of alpha.
They have a
Anyone
moderate.
else? Sorry?
They have a moderate wavelength.
I didn't get that. They have a what?
Moderate wavelength.
Okay, they have a modulative wavelength. Okay, so basically, since we looked at the alpha particle illustration, this one can also drive us to where we want to go by using the same properties. So of course, we look at it having a higher penetrating power than the what? Than the alpha particles. And of course, for it, it's negatively charged. And then we notice that it's represented by a negligible mass. And then we also have that as its atomic number. So it's represented as an, should I say electron? Yes, with a -1 on its atomic number and then a negligible mass. And then we also know that it's deflected on the positive side of the magnetic. Please and please, if you're not saying anything or if you've not been chosen, please mute your mic. I don't want to restrict us to muting our mics that I am the one who unmutes you. That's why I want us to do that due diligence. We are senior 5, so I want to treat us that way. So please, if your mic is unmuted, please and please mute because it sends feedback and distorts my explanation. So thank you. So when we have the beta particle, those are some of the properties that we look at. Okay, so then when we look at the gamma rays, what are some of the properties that the gamma rays have? So gamma rays, first of all, are represented with that formula. So what properties do gamma rays have? Yes, Nelly?
They have no charge.
They have no charge, very good. Rebecca?
They have the highest penetrating power as they move with almost the same velocity of light and energy.
Okay, that is good. So they have a very high penetrating power, which is compared to that of light. Any other? Okay, I'm seeing some responses in the chat. Maybe I should check them out. So they have a high energetic power. They are not deflected. Yeah, so because you remember we've said they have no charge, that means for them they are not deflected on a magnetic field or an electric field. Okay, so basically those are some of the important things that we are going to interact with in this lesson. So of course, as we disintegrate a particle, we expect energies of energy depends on what we are going to look at. So I'll share the notes that I wanted us to look at. This is history. Of course, I won't go into it. If you really want to read the history, you will go ahead and download the book and you can use it to get that history. Okay. So I am trying to get to where radioactivity is. It seems my mouse is responding accordingly. Okay, so here we have some of the properties that we've looked at. Okay, so this is the deflection bit that I was talking about. When you're looking at the deflection of the alpha particles, you notice that they will be deflected off in the negative direction of the magnetic plane. So when you're deflecting the beta rays for them, the beta particles for them, they will be deflected to the what? To the positive. And because they have a higher penetrating power, you also realize that their deflection will quite take place at a point like this. So it will be further than the alpha, which are deflected off faster. Then when you look at the beta for them, they will be deflected off in the positive direction. And then the gamma rays are not illustrated because they are not deflected because of their not having any charge on them. Okay, so here we come, radioactivity. And of course, like I said, this is history that I don't really want to dig into for now. Oh God, how do I move this? Okay, so the definition of radioactivity is down here as the spontaneous disintegration. And like I told us, these words are important and very key in our discussion. So we have the spontaneous of heavy and stable. The words I'm underlining, please make sure you never leave them out as you explain. So you may not give us the particles that are being given, but at least you should tell us with the emission of radioactive particles, full stop. So you may not list them because of course we already know what those radioactive particles are. Then of course we have the different types of radiations, which we've looked at, the beta, the gamma, and then the alpha. And of course, this is just showing us the different, what is the nature of those particles, like we've already stated. So in this case, we have the beta particles, which are represented with a negligible mass of 0, and then an atomic number of -1. As we are going to see in the calculations, why this happens the way it does. So we'll have beta particles are streams with high-speed electrons emitted by unstable nuclei. And of course, these electrons do not come with extra nuclear particle. And then the beta particles are distinguished from electrons by their source and their high energy. So that takes me to the next page where we have the alpha particle, which we said is represented by the helium atom, which has 4 and 2. And then, of course, the alpha particles are a stream of helium, and they're emitted with high energies from radioactive atoms. And of course, this is just the description. And then we have the gamma rays, which have negligible mass and negligible mass number. So, of course, for them, they have a very high penetrating power with a lot of energy. So we'll see even in the calculations that these ones don't really cause a change, but they are emitted because of the kind of energy that is being emitted by that given nuclei at the point of disintegration. So this is just a summary of the different characters that these different atoms have. So because the beta ray, we've already seen that it has a -1. So that means its charge is -1, so it's negatively charged. And when we look at the alpha, it's +2 because of the atomic number. So that means we have a positively charged alpha particle. And then of course the gamma rays, their charge is 0. They have no charge. So those are the different rates at which they move. So you can just take a screenshot maybe to look at those properties in details, but otherwise that is what we have there. Then of course we have they are deflected towards the positive pole in the electric field and also in the magnetic field. And then of course they have higher penetrating power. So these are just a summary. Then we have low ionization power.
Mute.
And then of course, since the alpha particles have a low penetrating power, that means they have a higher ionizing power. And then for the gamma rays, since they have a higher penetrating power, that means they have a very low ionizing power. So for the beta particles, for them, they have a moderately high ionizing power. So, but it's not higher than that of what? Of the alpha particles. Okay, so then we move on to the radioisotopes. Remember, when we are looking at atoms, we know that some elements have isotopes. And of course, if we relate with the knowledge that we had in O level, we know what isotopes are. These ones have different mass numbers, but same atomic number because of the differences in the number of neutrons. So in this case, when you have radioisotopes, they are also atoms that are unstable with the same element with the same number of protons but different neutrons that undergo spontaneous disintegration to form lighter ones with emission of radioactive particles. So we also have what we call the nuclear reactions. These nuclear reactions are the ones that involve the breakdown of these radioactive atoms into the different disintegrations that we expect to get. So I want us to look at the calculations of those nuclear reactions with emission of the beta, alpha, and other particles. So this is just to show us the difference between chemical reactions and nuclear reactions. It's basically for you to know what these chemical reactions are and what the nuclear reactions are. but in most cases, it wouldn't be a question to look out for, but it's important for you to know what happens. So we have the nuclear reaction, only the valency electrons are involved. While when you come to the nuclear reaction, sorry, there is a change in the composition of the nucleus. So the nuclear reactions really have to do with the nucleus, while for chemical reactions, we expect the reaction to take place between the valency electrons, because even when you're writing their formula, you're looking at what is the valence of carbon, what is the valence of oxygen, then you write the formula of carbon dioxide. So it really has to do with that in chemical reactions. Then elements don't lose their identity. When you look at a nuclear reaction, completely new elements are formed. So for example, if there is a disintegration of a sodium atom to form, let me say, magnesium, sodium is not at all related to what? To magnesium. But when you're looking at a chemical reaction, those elements should remain within the compound that they are what? They are forming. Then when you look at the number of protons and neutrons in the atomic nucleus do not change. So that means the way the nucleus is formed, because remember when you're looking at the O-level chemistry, protons and neutrons are inside the nucleus. That means they are not distorted. Even in the reaction, it's electrons taking place in the what? In those reactions. But when you come to the nuclear reactions, because you're dealing with the nucleus, that means the protons are changed either to increase or decrease depending on the type of emission that they have undergone. Then, of course, small energy is involved, but when it comes to radioactive substances, you need a lot of energy. Then when we have the external factors that affect the reaction, which is temperature, catalysts, and all those things. When it comes to the nuclear reactions, it becomes the instability of this atom is what causes it to disintegrate spontaneously. But you realize that catalysts and pressure changes do not really affect it. And then, of course, for some chemical reactions, there is always a reversible change, because you've seen those equations with double arrows where we can obtain back the reaction. But when it comes to the nuclear reactions, for example, if we're to look at the tombs of Egypt, the kind of wood they use, once it disintegrates, you cannot reform back that wood. So the reaction is irreversible. Once there is disintegration, that is it. And then, of course, isotopes undergo same reactions, but here on nuclear reactions, the isotopes give different products in the nuclear reactions depending on what type of emission it has undergone. Okay, so I hope that is clear to all of us. So here we come on some of these reactions. So for example, I can give us an example here. When we are emitting an alpha particle, we expect that we have, for example, here we have X, which is A, and then B, giving us, because remember it's an emission, that means we have helium being given off plus C and dy. So when you look at these, this one is being given off with this. So that means A was reduced by what? By 4 to give us C. So that means in order for me to get C, I have to subtract A minus 4 for me to get the C, such that even when I am writing my equation, it is well balanced. The same way we had chemical reactions being balanced, it's the same way we have these nuclear reactions. So that means the atomic masses of this and this added together should give you A. And then the atomic numbers D plus 2 should give you B. So that means for me to get B, for me to get D, I had to subtract B minus 2 for me to get the D. So that is what that emission tells you. So in some cases, they may give you Y and they give you X, and they need you to find that type of emission that given reaction underwent. Or sometimes they'll give you this and that, and you need to find the values of C and the values of D. So when it is a gamma reaction, for example, if a gamma particle is being given off, because remember we said for gamma, there is no change in the atomic mass and there is no change in the atomic number. So that means if there is no change, A will be equal to C and B will be equal to D, because gamma rays are given off as a result of a lot of energy and their high penetrating energy. Sorry, they are high penetrating power, but they cause no changes on the atomic mass and on the atomic number. That means that the changes in masses are not there. Then when we go to the beta, when we go to the beta particle, sometimes they may actually represent it as beta as it is. So it's up to you to know that beta particles change in mass, in atomic number by -1 and change in mass by a negligible amount. So that means the mass will remain the same while the atomic number will be affected by this -1 depending on what type of emission it is. But then also, as we look at the beta emission, we also have what we call the electron capture, which is also called the Brisson. I don't know if we've heard of that. So we also have an emission which is called the electron capture. But in electron capture, the same way you hear capture, that means the electron is being captured. As well as here we have a beta emission. When it comes to electron capture, the electron is not after the arrow, it's before the arrow. That means it's one of the reactants because it's being captured in that type of emission. Are we all together up to that point?
Yes, teacher.
Okay, thank you. I want us to look at some examples that contain the different, of course, here you're supposed to have a periodic table. So I hope we have periodic tables with us. So this is just an illustration of those particles. So for example, we have an electron here of bombardment. So when we have for example, we know that sodium has I'm going to just give us an example to try out. We know that sodium, what is the mass number of sodium?
23.
23, very good. And then what is its atomic number?
11.
11, very good. So if sodium undergoes an alpha particle emission, what new product is it going to form? If sodium undergoes an alpha particle emission, what new product is it going to form?
Aluminium.
I'm waiting for responses. What? Sorry?
Aluminium.
Aluminium. Okay, how did you get that? How can I complete this equation?
Since it's reacting with an alpha particle, that means you have to add 4 to the mass number and 2 to the atomic number. So when I added that, I got 27. That's the mass number. Then the atomic number, I got 11. So when I looked into the periodic table, 27 is for aluminium. Then I completed it with aluminium.
Okay, so thank you so much. So what happens here is the new atomic number that you form is what helps you find the element that you are looking for. So like the same way we identify these elements using atomic number and not mass number, it's the same thing we do for radioactive atoms. So in case I have added that I know that if I know that wait, have I done the right thing here? No, this alpha particle is supposed to be this side. So here you notice that if I were to get an alpha emission, that means in this case, I have, for example, if I had X here and Y here, and then maybe I'm looking for this atom, that means I'm going to have, because remember I said an alpha emission, so that means I'm going to have 23 is equal to 4 plus what? Plus X. So what is going to be my value for X? I am going to have 23 minus 4, which is equal to what? To X. Because I'm subtracting 4 on both sides. So 23 minus 4, what does it give me?
19.
Sorry?
19.
19, very good. So that will give me 19 is equal to what? To X. So then I come to Y, which is 11 is equal to 2 plus what? Plus Y. So my 11 minus 2 is equal to Y. So what is 11 minus 2?
9.
9.
9, very good. So I'll have 9 is equal to Y. Such that when I come to this point here of having 19 and then 9, and then I have to find my element there. Remember, like I said, please mute if your microphone is unmuted. So we have Y plus 2, it's giving me 11. Because remember, what I have on my right hand must balance with what I have on my left hand. The same way we have equations being balanced, it's the same thing we have here. The atomic number should be able to give you the same number this side and the atomic mass the other side. So it should be able to give you a common value. So what element in the periodic table has an atomic number of 9? That is the element we put here. So which element is that?
Fluorine.
Fluorine.
9. Atomic number 9 is chlorine. Senior
Fluorine.
5s. Fluorine. Okay, very good. So we have fluorine. So that means our element there becomes what? Fluorine. So you must be able to differentiate between a bombardment and then an emission. An emission means you gave off that. And then when you bombard, that means it reacted with that element. So that is what you get at that point. So I have another example for us. If we had an aluminium particle, what is the atomic number of aluminium?
13.
13, very good. And then what is its mass number?
27.
13, then 27.
27.
So if aluminium undergoes a beta emission, what product are we going to form this side? Let's all try to calculate it and see what we get. If aluminium undergoes a beta emission, what product do I expect to get? Silicon. Okay, I'm saying silicon. So that means we are going to have our beta particle with -1 here and then 0 there. So that means plus 27 minus 0 still gives me what? 27. And then 13 minus -1 gives me what? 14. And of course, I go to my periodic table, I look for what element has atomic number 14. That is the element I attach there.
Silicon.
Yes, so I hope we are now together at that point. Okay, so now if I have, for example, nitrogen, what is the atomic number of nitrogen?
7.
7. And then atomic mass?
14.
14, very good. So if it undergoes a gamma emission, what do I expect it to become?
The same element.
Okay, so it will remain as nitrogen. Because remember, we said for gamma rays, they don't affect the mass, they don't affect the what? The atomic number as well. Okay, so should have some activity down here. So I want us to try out that activity. So we have an activity here that I want us to try out. So there is this activity here. Name particles 1 and 2, and then identify X, Y, and Z, then state the groups to which X, Y, and Z belong. So let's try it out so that you can give me your responses in the chat if you're through. Okay, I can see the chat. Someone is saying particle 1 is a beta particle. And of course, you can notice that by looking at the change in the masses, in the atomic number. So when you look at the atomic number here, it's 82, here it's 83. And the atomic mass has remained the same. So that means that we have a beta particle, which is E0 and that. And of course, someone can also represent it as beta. And then the second one, I saw in the chat someone saying alpha particle. Okay, that is good. So the alpha particle is what we have here, because when you look at the changes in the masses, we have 83 here, and then we have 82 here, 81 here. So that means there was a +2 on this other side. And then this side, we realized that 4 was subtracted as 1. So the second one is an alpha particle. So you can either put alpha particle or you put the helium molecule there. Put the 4 and then the 2. And what is element X? What is the identify element X? Of course, now there you will have to go to your periodic table and look at which element has 83 as its atomic number. So after reading off which element has 83, you generate what element that is, and you're able to identify it. Yes, so it is Bi, which is bismuth. And then when we go to Y, this is 81. So go to your periodic table, look for the element that has atomic number 81. Is it TiTl? Okay, Y is xylem. So that means when we get Z, what is going to be the composition of Z? What is its atomic number? What is the
82.
atomic number? 80 what?
82.
82, good. So we have 82. And then what is its atomic mass?
208.
208, good. So which element is this?
Lead.
Lead.
Lead. So we have Pb here. So that is what we'll have. So you realize that these are simple things. We are all getting them. Yes, Phoebe.
Madam, me, I'm not getting it because I thought, yeah, negative like 81 minus 1, yeah, you get 80. But why are you getting 82?
80 what?
For me, I thought that the answer is going to be like atomic mass is going to, no, atomic number is going to be 80 because the beta particle has -1. So 81 minus 1, you get 8. I'm not getting it how you are getting 82.
Oh, yeah, you're right. So thank you for taking note of that. So when we have a beta particle being emitted, that means the other side we have 81, which is equal to -1 plus. But now if we have 80 here, will it really give us the 81 we are looking for this side? Because remember, what we have this side must balance off with what we have this other side. So that means it's going to be 82. So that when we subtract the 1, it takes us back to what we have this side. Is it making sense?
Yes, it's making sense.
Yeah, so you're supposed to make sure that at least those equations balance, that what you have on mass number the other side should give you what you have as mass number on the other side of your left hand, depending on what kind of emission that is. Okay, so let's move on to the next. So we have a few terms here that I want us to quickly go through just to check ourselves on what we've gone through. I don't know if I'll be able to compile for us some questions on these radiations. Okay, so remember we said that is why we are not using the mass number to determine, sorry, the atomic mass to determine the positioning of those elements. Reason being, we may have isotopes where we have the same atomic number but different mass numbers. Because remember, when there is disintegration, there is a change that comes about. That is why this side we are able to obtain lead that has this kind of mass compared to the actual lead that we know, because there was a disintegration to give us that kind of atom. Hilda, I don't know if I've answered your question. So you may not specifically say that lead has an isotope, which I got from my calculation, but it's about telling you about the disintegrations, the different changes that occur when disintegration takes place. Okay, so those questions are for you to test yourself and find out what you've understood from this lesson. But I'm more interested in these calculations here. So I want us to go through calculation per calculation so that we are able to know if we have actually understood what we had the other side. So of course, like I said, we have the different emissions that you may keep on coming across. So for example, this is the neutron emission, and then of course the other few, as we go about them, I will let us know what they really represent. So can we try out these calculations? I'm giving us 5 minutes to try out the first. No, let me just give us a round figure. How many minutes should I give us? Let's suggest, but they shouldn't go beyond 7 minutes. Because I know at least everyone here is very alert and they are going to really do the numbers very fast. So how many minutes should I give us? 7 should be enough. So that means, okay, someone is suggesting 5. Okay, that's nice. So at 5:14, I'm going to be asking us for what we've been able. Hilda, 20. No. We don't have 20 minutes, sure. Calculate those numbers. So I'm giving us up to 14 minutes past 5. So let's calculate and see what answers we come up with. Stella, what is not clear enough? The explanation, the work, what is not clear? Because the dashes are explaining that you have to fill in the dashes according to. For the E here, this E, you have to identify which element it is. So you find out what is E according to this equation. And then here you find out what is G according to this equation. And then here, the dashes up and at the bottom of silicon and at J, they are asking you to identify what is the atomic number of silicon and what is the atomic mass of silicon. Then after this beta emission, what do you get as the atomic number and as the atomic mass? So it is just communicating that. I don't know if that is much clearer. So here, basically, in the first assignment, you're just getting for us the atomic mass and atomic numbers. Then when it comes to the second exercise, you're writing the actual element according to the kind of emission that has taken place. So I hope that is clearer. Stella, is that clear?
Prestige.
Okay, so someone is asking on number 3, on Roman 3. Roman 3, that is supposed to be a negative because remember it's an emission. It's not a capture. So please change that. Thank you for taking note. Because at least if it was this side of cell phone there, it would be okay to have a plus. And I think we should be winding up because we are 2 minutes past our time that I gave us. In fact, 3 minutes now. So that means at 5:20 we are going back. Hey, Mildred, where are you now if you're not doing all of them? Because that's why I gave us the 7 minutes.
And the award for Best African Magic Original Telenovela goes to and the winner is Ompali.
Sarah, are you in class with us or you're somewhere else? Because the things you're getting in the background might be distorting people's chemistry. So at 20 minutes where we'll have stopped is where you can copy the rest and do them later, but you need to move. So we still have 2 extra minutes to wind up with whichever number we are at. Okay, so I think that time is enough for us. We can now go through very fast what we've done, and then we can move to something else. Lindsay, when you're getting the element, you look at the mass, at the atomic number. That is what helps you generate it from the textbook. sorry, from the periodic table, but not looking at the what? At the mass number, because the mass number may not be as accurate as what is shown in the periodic table. So what happens is you look at the atomic number. That is what drives your knowledge to what element it should be. So your focus shouldn't really do with the mass number, but to actually focus on what the atomic number is. I hope that is clear. So let's quickly go through. So for the first one, what was the mass number for E? Yes, Rebecca. Anyone who is ready to tell us, please go ahead so that we can move.
5.
What mass number did we get?
5.
5, that is good, such that when we add 5 plus to this side, it gives us 7 plus 0. Then the mass number?
14.
10.
Okay, good. So it's 10.
14.
Madam, it's 10.
Yes, it's 10, because when we add 4 plus 10 this side, it should be able to give us the 14 we have this side, 13 plus 1. So that means we get 10 and 5. So if you got that, bravo. Then we move to the next one. What did we get as our mass number on G?
Excuse me, madam. Do we have to like tell what the element is since we found its mass number and its proton number?
You can for your revision's sake, but this question was basically asking you to get the atomic masses and atomic numbers. But for better revision, it's good for you to know what element it is, because it guides your study better.
Okay, please. Thank you so much.
Okay. Yeah, I said for number 3, change this positive to become a negative. I think I made that correction on number 3. Then for G, what was our atomic mass? People, let's unmute and contribute, because I don't want to keep checking the chat for these responses, at least for the
10.
rest, but 10 and what? 10.
Madam,
Does that give us 10? Maybe the
I
atomic.
have the atomic mass. I have 25 and atomic number 12.
25 and atomic number 4.
12.
Okay, such that when we subtract this side, it still gives us 11 the other side. Okay, that is good. Then we move to the third one. What was the atomic number of silicon?
Madam, that number confused us because there were
14.
two numbers without the atomic mass and atomic number.
But remember, in your periodic table, you know what silicon is. So you know that it's
Teacher.
14. Then what is its mass number?
28.
28. So you just had to go to your periodic table, find out what does silicon have as atomic number and what does it have as its atomic mass. So for it, you had the element there. So you just had to identify those from the periodic table.
Teacher, teacher, small question. Is it a positron on number 3? Number 3, isn't it a positron?
Is it a what?
A positron.
But remember, positron is the same as you having a proton capture. So it has to be the other side where silicon is for it to be positive.
Oh, okay.
Yeah, because
So,
a positron is the same as electron capture. So it acts as a reactant, not as a product.
no, teacher, could you look at page 1 positron? It's also on that side, like it's on the other side.
On the other side of the
Like after the arrow, it's after the arrow.
Okay, I think maybe there must have been a mischief or something, but when you're looking at the electron capture, it has to cross over to come to, because you're capturing that electron, you're not emitting it. I don't know if you're getting my point.
Yes, teacher.
Yeah. So what was the atomic mass for G?
Was 12.
Atomic mass, not mass number.
We got 13.
Really? When we have silicon, which is 28 here. So that
Sorry.
means,
You say G.
28.
You say G.
but there is no G. Okay. J, okay, sorry.
It's 28.1.
15.
So it's 28, then the atomic mass, sorry, the mass number.
15.
Sorry?
15.
15, yes, because we've changed this to be a negative. So then we go to the next one. What is the atomic number for Q?
That's 15.
14.
Atomic number for Q.
6. 14.
6.
People, let's not confuse atomic number with mass number. What is the atomic number for Q?
6.
6.
6, very
6.
good. And then what is the atomic mass for R?
1.
1.
1. Okay, good. So this one can also be called a proton or a hydrogen atom. So in most cases, you'll find when it's represented as P, 1, 1, or as hydrogen, 1, 1. So when you meet those, don't get mixed up. Okay, so we go to the next one. What is the atomic
Pardon,
number for W?
teacher, pardon, on R.
I said R, which is 1, 1, is also a kind of emission, which is maybe emitting a proton. So when you're emitting that proton, it's represented as P, 1, 1, or as hydrogen, 1, 1. So when you meet that kind of emission, you also work with it the same way you worked with the rest, where you have a change in the atomic mass as 1 and the change in atomic number as 1.
Okay, thank you, teacher.
Welcome. So what is the atomic number for W?
8.
8.
8.
Okay, that is good. And then for X?
1.
1.
1. Very good. And then we move on to the next. What is the atomic mass of Y?
207.
207.
7. Very good. Then we move on to the next. What is the atomic number of Z? Remember, there is a 2 in front there.
2. 2.
2. Very good. Such that when you multiply 2 times 2, it gives you 4. 3 plus 1 gives you 4. And then the atomic mass?
4.
8. 4. 4.
4. Okay, very good. So that means that was a helium particle, which was multiplied by 2. So you will find in some equations that in order to balance them, you need that 2 in front of the what? Of the helium particle. So don't get restricted that only helium appears only like this. So in order to balance that equation, sometimes you may need to add a factor in front so that you're able to get the required number of particles that were lost on a particular number. Okay, so then we move on to the next assignment. We have RA. So what is going to be our atomic mass for this molecule?
86.
Sorry?
86.
86.
I asked for atomic mass. Now you people.
222.
22.
Okay, which element is this with 86?
Rn.
Sorry?
R A.
R what?
Rn.
Rn.
Okay, thank you. Then we move on to the next. We have N7. What is the atomic number?
8.
8.
8. Very good. And
8
then
mass.
16.
that 16. What element is that?
Oxygen.
Oxygen.
Oxygen. Good. And then we move to the next. This one. So it's a beta particle. That means we are emitting -1, 0. So what are we going to get as the atomic number?
7.
7.
7. Very good. And then mass?
14.
14.
14. And what element is that?
Nitrogen.
Nitrogen.
Nitrogen. Good. And then we move to the next. What particle was bombarded to that?
It was a beta particle.
Okay, it was a beta particle where we have E, -1, 0. Okay, good. Then we move on to the next. Cobalt, what are we going to get?
The element is interest.
Then atomic number 28.
Atomic number?
28.
28. And then atomic mass?
60.
What element is that?
Nickel. Teacher, it's nickel.
Then the next?
We have 90 as the atomic number.
90.
Then 234 as the atomic mass.
The
Okay,
element
good.
is TH.
TH. Okay, good. And then we move on to the next.
We have 93 as the atomic number.
93.
Then 238 as atomic mass.
And
200
element
what?
is NP.
238.
And then the element is?
NP.
The next? What is the mass number?
41.
Mass number.
43.
97.
Mass number.
95.
97.
97. Then atomic number?
43.
43. What element is that?
TC.
TC.
Okay, thank you so much. So those are the answers we expected you to come up with. So you can go ahead, get the question bank and try out more examples, because at least every paper one of each year has some of those numbers. If it's not there in paper one, then in paper two. So at least every year you expect radioactivity to appear somewhere. So you get a question bank and try out. I hope we are all together up to that point.
Yes, madam.
So
Yes, teacher.
these ones, just take a screenshot, you try out in your free time. I am not giving us time to do them. So you have just a minute to take a screenshot of these other examples on top of the ones you'll find in the QB. So I'm hoping we are done with a screenshot. And then the other part of the questions. Take this as a screenshot as well and try it out in your free time.
Madam, I was begging if you can scroll back and you also take the screenshot of the other number.
Okay, so those using a laptop, you press Control, then Alt, then Part Screen. You press those three buttons at the same time, it should be able to give you a screenshot of what you're looking for.
Those using smartphones.
Those using smartphones, it depends, because some screenshots you can just swipe on your screen with a definite number of fingers, or you can check in your notification bar. There is always that icon of screenshot. So I don't know what kind of phone you're using, so I can't tell. But at least your phone has that setting of a screenshot. Some just double tap and maybe it presents the screenshot. So for the laptop, you press Control, Alt, and then Part Screen. So at the same time, it should be able to give you the screenshot. So I hope we are done with this one as well. Taking us back to the last part, and then you take a screenshot and you move to something else. Please try out the numbers, don't keep them. And those who would have taken, I don't know if your groups are open, you can post the questions, the screenshots of those questions, or share with your friends, those who are not able to take the screenshot as per now. And I think Mr. Kaziwa also posts these videos on YouTube. So you can go back and forward the message, and forward the video to where the questions are, and you're able to copy them at your convenience. But now people with music, Bambi, spare our ears. Okay, so we have this formula here that I want us to know at the back of our minds. I am not going to explain how we get to this formula because I was advised not to for some reasons. So it is better for us to know how this formula operates and know what the formula is. But of course, if you read, you can always get the explanation to why that formula comes about the way it does. But it's an important formula because every time you're calculating radioactivity, we expect you to denote it. You have to write it before you go ahead and calculate. So okay, anyways, so you have the ln. Ln is a mathematical term that can also mean 2.03 log of a given entity. So on your calculator, when you look at your calculator, you have that ln thing next on the log button of your tab. I think it's EX, where you have E power X. You have that ln tab. So When you see this word ln mathematically, it is the same as you writing 2.303 log 10 of that given entity that you're working with. Then, of course, N naught here is meaning the original mass of that radioactive substance. I expect that maybe you're writing them somewhere. So this is original mass of the radioactive substance. And then this is the mass after decay of time t. At time t. Infinix Vanange. Okay, so we have mass of decay at time t, and then this what do they call this formula? Do I still remember the name of the lambda stands for the decay constant. I hope you're following because I'm writing things everywhere. So this is decay constant. And then T is the time taken for the radioactive substance to decay. So we have T as the time taken for the radioactive substance to decay. So when you look at what I've circled here, 2.303 was situated where the ln was. That's what I say. That if, for example, you are told to calculate the decay constant, you have the original mass, you have the time taken, and then you also have the decay constant, and then you're finding T. Or at least when you read the question, it should be able to drive you to what you're finding. And of course, when they use counts, because when we are dealing with radioactivity, we deal with masses and counts. So if you find that the question is telling you counts, where there is N, you always put C naught, which means the counts, the original counts before decay. Then CT means the counts after decay. Then of course the rest remain the same. Here you will have your ln, which is equal to lambda t. So at that point, when the question is saying counts, you use C instead of N. When it's talking about masses, you use N. So that is something to have at the back of your mind. Okay, so someone is asking to send a video. We cannot send a video because it's a YouTube video. So just go and look for help lessons on YouTube. You'll find all the videos, even for the previous lessons that you've been learning. They are all there. Actually, I think I was watching one yesterday. So you can go there and just go to your YouTube, search for help. I think it's holistic e-learning platform, online lessons. Yeah. They'll be able to avail for you and you will see the senior 5 video. Yes, Quera.
Excuse me, teacher. Is it necessary to note like how you come up with those formulas, or it's just important to know the formula in your head?
It's important for you to know the formula in your head. That's why I've not gone through how the formula comes about. But if you're interested, really, your teacher will do that at school. Because it's quite a lengthy method and it requires me to bring in some math concepts that you've not yet covered, which some of us may start asking questions and we may take a lot of time there. And since in the exam, it can't come for you to prove it that way. But as scientists, we are not supposed to just assume. We need to know where those things come from. That is why it's important for you to know how it comes about. But otherwise, it's important for you to know the formula as the formula, because for every calculation, you need to suggest it before you go ahead and calculate.
Okay, thank you.
Yeah, by the way, Mr. Kaziba always posts those YouTube links on the groups. So if you're on the groups, just wait for the links. He'll show them, he'll post them there. He always posts them. But me, since I subscribe to the channel, every time a new video is uploaded, it comes up on my top watch videos on YouTube. So even you, when you watch a video, like it, share. It will always give you those notifications on your YouTube about the lessons. Okay, so before we close today, I want us at least to use this formula to try out a question. So let's first see. So this is just a summary of the different expressions that you can have depending on what the question has asked you to find. So because remember, this formula is also to guide us on how to obtain the half-life of these different substances. Because remember, if we have radioactivity, then we expect to have the half-life of that given substance. So when we are dealing with the decay constant and then the original mass and then the mass at time t, we should be able to also know what half-life is. So who has an idea on what half-life is? You can just briefly explain to us what you think half-life is. Yes, Farah?
I think half-life is the total time taken for a radioactive substance to decay to half its original mass.
Okay, that is very good. So half-life is that time taken for a radioactive substance to decay to half its original mass. So that means if it's decaying to half its original mass, that means you'll have your time t. Because remember, we are coming from this formula here. Remember, we said our formula is ln of n naught over nt is equal to alpha t. But remember, this time round, we are looking for half-life. So if half-life is the time taken, that means we denote it as t half. So at this point where we have t, we'll be writing as t half just to show us that we are looking for half-life. So if we have this, and we know that it's the time taken for as radioactive substance to decay to half its original mass. That means if we had NO at the beginning, for us to obtain time t, that means if this decayed at time t in this formula, now since we are looking at half time, that means our original mass will be N naught, NT is equal to N naught over 2. Do we all get that point?
Yes, ma'am.
No, madam, we are left behind.
Okay, I've left some people behind. Okay, so I'll repeat this one more time. Remember, we've said in our original formula of finding the decay constant of a radioactive substance, we said the formula is ln of n naught over nt is equal to lambda t. But we say this nt means that mass you have at that time of decay. But when you come to half-life, because you're looking for the time taken for that radioactive substance to decay to half its original mass, in this formula, this T will become T half to show us that we are looking for half-life. And because here we had NT, the mass that decayed at that time, and the original mass, which is N naught, that means when we are getting the mass at half-life, it means we will have NT is equal to N naught over 2. Are we now together? So the original mass is halved. Sorry, I didn't get that.
Yeah, we are together.
Okay. So the original mass in that case is halved, because remember we said it's the mass, it's the time taken for that radioactive substance to decay to half its original mass. So that means where there is NT, we are going to put N naught. So we have ln of N naught over where there was NT, we are now going to put this. We are now going to put this one here. So we'll have N naught over 2 is equal to lambda of T half, because this is half-life.
I beg your pardon?
Where?
Starting from the ln N naught out of N naught out of 2.
Okay, I said, remember this is the formula for finding the decay constant or the time taken for radioactive substance to decay. But now when we come to half-life, we expect that the mass that we had is reducing by what? By a half at T, at half-life time. Are you getting my statement there?
Yes, I am.
So if it is reducing by half, that means where we originally had NT at time T, now where we have half-life, we have the original mass being halved for us to get the half-life. So that is why in this formula where there is T, I wrote T a half, and where there is NT, I took the mass that has been halved. Are we now together at that point?
Yes, madam.
Okay, so now after getting that, we know that our ln of this one, you can do it mathematically, N naught times 2 over N naught is equal to lambda T a half. So because these ones are the same, the numerator and the denominator cancel, and then we'll remain with ln 2 is equal to lambda T and a half. So that means this is the formula we use to calculate the T and a half. Or some people even write as T and a half is equal to ln 2 over lambda. So this becomes the formula that we use to calculate half-life. But of course, like we are going to see in the calculations, you have those different substances responding differently. Let me just try to write here first. Okay, let me first see what to do. Let me show you. So when we have half-life, like I said, we have the original formula as a half is equal to ln 2 over lambda. But remember we said ln is the same as having 2.303 log. So I want you to press on your calculators 2.303 log 10 of 2. What answer does it give you? Anyone with a calculator, please press that into your calc and tell me what you get.
0.693.
0.693. So I'll stop there for now. Over lambda. So this formula is what we actually use to find the what? The half-life. But if you can't remember this value, you just write ln 2 over lambda. But in most cases, some people just go direct and say T1/2 is equal to 0.693 over lambda. So that is still okay when you're calculating half-life. So it's important for you to know this formula and to also know the one for ln of N0 over NT is equal to lambda T. So this one is for calculating the radioactive decay. Then this one is the half-life equation. You can either use this or this.
Madam,
So students, yes, please.
no, I was asking like, in physics we also learned half-life. What if I use that formula of physics?
Of course, the formula of physics is okay, but you have to just make sure that it gives you the same responses as the methods that we have here. But it's still okay. Is that clear, Ahumuza?
Yeah, it's clear.
Okay, so lastly, I want us to just look at how they calculated it here. So you can see they are showing that when N0 decays, so it's showing that when N0 decays to half its original mass, then T is equal to T1/2 and N is equal to, NT is equal to 1/2 the original mass, which I explained. So we have this equation here, and they are substituting in the half-life terminologies. So we have ln of N0 over 1/2 of N0 is equal to lambda T1/2. So ln of 2 is equal to lambda T1/2, which is the same as me having T1/2 of 0.693 lambda. So it's more like the same way to calculate those half-life equations. So we have a question here. We conclude, I want us to try it out so that we can at least have something we've tried out before we exit today. We have just 2 minutes, so let's calculate it very fast, and then you can share your answers in the chat. Immediately you're through, you can just share your answer in the chat so that we can go over the number and then we can call it a day. Anyone that is through?
I have 9.3.
9 point?
9.33.
9.33 days. Because remember, you need to have the formula of those different substances. Okay, so first of all, you need to understand that we need to find
The constant.
Yes, you need to find the decay constant. Very good. And then after finding the decay constant, you feed it into the half-life formula in order for you to get the what? The half-life. Okay, that was very good. So I don't know how many people got what you got. Okay, so like for example, you can see here counts. So like I say, denoting the formula is very important. So you can see ln of counts naught over counts of t into lambda. And then of course, this was counts naught, and then this was counts t, and this was the time. So you realize that also the decay constant must have units. And because it's an expression of a fraction, it becomes per day. So that means it's day per that. If you don't have this, you lose a mark for this point. They will mark the rest of the work, but you will miss the half mark here. And you know every half mark in chemistry counts. So ensure to put the what? The units. Then you come and feed into the formula. Then you can approximate. Always first give the answer you've got, then you can always approximate thereafter. So basically, that is how we calculate half-life. And I think now you can appreciate why we needed to know the formula of a radioactive substance before we got into the half-life. Okay, so that's all we had for today. If we have no questions, I'll request someone to pray for us in closing, and then we can begin from there. I think I'll compile some questions and post them for us to try out before our next lesson. Because our next lesson is most likely to be on Monday if there are no changes. So you can plan for Monday. Okay, it seems there are no questions. Can someone pray for us and we call it a day? Yes, Phoebe, since your mic is unmuted, please pray. How about seeing your face? Why you don't want to pray? What happened? People, let's pray so that we can close, so that you can go and rest and then plan to read. Yes, Mildred.
Okay. Let's end our whole part with prayer. Almighty God of King of Father, thank you for the gift of this season. Father, our prayers are going to our different places. May you guide us and our whatever Madam has taught us as is in our heads. It's going to say that we're going to use it to our own benefit. The prayers are in different places. May you protect and may you guide us, Father, and all may be
Amen. Thank you so much, Mildred, and thank you so much, everyone, for connecting. Have a blessed evening.
Thank you for also teaching us.
You're welcome.
Thank you for that.
You're welcome.
Thank you.
You're welcome.
Thank you, madam.
You're welcome. Thank you.